Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at section 8.1, which is the start of chapter 8. For the past few videos, we've been spending a bunch of time working with infinite series. In chapter 11, we studied the behavior of infinite series, namely whether or not infinite series converged or diverged. We also spent some time at the end of chapter 11 discussing how to represent different functions as infinite polynomials through the Taylor series and Maclaurin series process. Chapter 8, though, is going to be a bit of a deviation from that. We're going to be actually sort of stepping back to looking at further applications of the definite integral. So chapter 8 is going to sort of relate more to what we were doing earlier in the course with chapter 6, where we studied sort of uses and applications of the definite integral. If you remember back from chapter 6, we spent some time learning how the definite integral could be used to understand the area between curves, how it could be used to understand the volume of a solid of revolution, also how it can be used in physics to calculate work or calculate the average value of a function. In this section, we're going to be doing something sort of similar, seeing how the definite integral can be used to help us measure the length of a curve. So to do that, let's phrase our question so that we understand sort of what our goal is in this video. Then we'll do a bit of exploration, sort of summarize our results, and then we'll take a look at some examples. So first of all, as our sort of main question here, how do we measure the length of a curve? Or, put another way, how do we calculate the distance between 2 points if we follow a path defined by a function? Now, you guys all know from like basic geometry that if you want to measure the distance between 2 points, the straight line distance, then we have a very nice and easy formula that comes courtesy of the Pythagorean theorem that says if you want to measure the straight line or linear distance between x1, y1 and x2, y2, you just need to do the square root of y2 minus y1 squared plus x2 minus x1 squared. That's the distance formula. The question that we're doing here is a little bit more subtle. We're saying we're still trying to find the distance between 2 points, but we're going to follow a path that's defined by a function, namely a path that might not be linear. So our path might be parabolic. It might be defined by a quadratic function or something of that nature. So of course the distance is going to be different because we're following a different type of path. So let's see if we can sort of explore how we could study this idea here. So to start off with, let's see if we can just get a sort of visualization of what we're discussing here. So let's give ourselves an axis, and let's imagine maybe we have a curve like that, and we're going to say that we're going from some x equals a maybe to x equals b. So we can imagine if we wanted to, I guess we could label these points here and here. So since this is going to be y equals f of x, then since we've chosen a and b to be the ends of our x interval, I guess then this would have to be f of a and this would have to be f of b. And again, so we're just drawing sort of an arbitrary curve here. And of course, our goal is to measure the distance from here to here, but not the straight line distance, but instead the distance that follows this sort of curved path. Now, if you remember from geometry, we know that the straight line distance is the shortest distance between any 2 points. But we're going to be interested in the slightly longer distance that follows whatever this curve y equals f of x is. So how are we going to approach this? Well, we're going to take our standard sort of way of examining things when we want to build an integral, which is that we want to try to come up with an approximation that we can easily understand, and then let that approximation become a better and better approximation by cutting this thing up into smaller and smaller pieces, and then at some point, maybe that'll develop into a definite integral. So let's do our standard approach. We'll cut this interval into several pieces here, and we'll say that the width of each of these partitions as standard is delta x. So we're going to be cutting it up into delta x sort of pieces here. And let's just pick an arbitrary one somewhere down the line. Let's call this x sub k, and then the next one x sub k plus 1. So we're looking somewhere down the line where we're at x sub k, and then we're going delta x to x sub k plus 1. And let's imagine actually locating the sort of 2 points on our curve that correspond to that. So we're sort of looking here and here. Now, of course, we've done a lot of things in our class where we might like draw a rectangle if we wanted to measure the area, or we could draw a rectangle And then, if we were revolving, sort of imagine building like a cylinder or something like that. But of course here, we're interested in measuring the distance. Now, like we said, we don't have any sort of fancy formula, at least not yet, for the distance along an arbitrary function, but we do have a formula for straight line distance. So let's imagine that we're sort of putting a straight line component there. So let's see if we can at least first figure out what that straight line component is. So this blue, so our first goal is, I guess we can put it this way, first goal, determine straight line distance here. And then, of course, what we could sort of argue is if we did the straight line distance for each piece and added those all up, well, it wouldn't be exactly the length of our curve because all these straight line pieces are just estimates, but it would be a good approximation. So let's see if we can determine that straight line distance right there. Well, we can imagine that the ends of this straight line here, well, that end has got to be at x sub k and f of x sub k. And this one has to be at x sub k plus 1, comma, f of x sub k plus 1. So those have to be the points at the two ends there. So like we said, how do you measure the distance between 2 points along a straight line? Well, we have that distance formula. So we could say that that length there is the square root of the difference in their y components. So f of x sub k plus 1 minus f of x sub k squared. And then we'd have to add to that the difference in the x components, which would be x sub k plus 1 minus x sub k squared. And of course, what we're really doing there is we're measuring how far they are apart this way, how far apart they are that way, and then using Pythagorean theorem to get that straight line distance there. So that would be our straight line distance. Now, this is a pretty messy expression. I mean, it used everything that we have there, but we can actually phrase this a little bit more nicely. Notice we actually know this quantity here. I can't really say much about this, but I certainly know this. The distance between x sub k plus 1 and my xk, that by definition is delta x, because that's our spacing of these partitions. So we can say that this straight line distance is the square root f of x sub k plus 1 minus f of x sub k squared plus, and then in here, delta x squared. Okay. Now we're going to do something that maybe isn't initially super clear why we want to do it, but what we're going to do is we're going to begin, or take our next step, by factoring out a delta x squared out of the square root. So if we do that, we can get sort of a weird expression in here. What we would get is we could write this as f of x sub k plus 1 minus f of x sub k over delta x all squared plus 1 times delta x. Now, why is that valid? Well, it might look a little confusing, but if you want, imagine distributing this back. To distribute this back into the square root, you'd have to treat it as the square root of delta x squared. When you do that, it would come in here and it would give you that delta x squared there. And when it comes into here, it would cancel with this and give us what we originally had there. So this is a nice valid manipulation. Why is this a manipulation that we might want to use? Well, it gets this delta x outside, which we know is sort of a standard setup for for our next step, which is to build a sort of Riemann sum here. Okay, so the next thing we could say is that since we now understand that straight line distance, we could say the overall length of the curve is going to be approximately the sum of those straight line distances. So our second goal is to go ahead and build estimate for overall length of curve, which we will call L in black because, of course, our curve was originally the black curve there. Okay, so we could say that L is roughly the sum over all those x sub k's, this summation, which we are now very comfortable with, right? So the sum of all these sort of pieces here. F of x sub k plus 1 minus f of x sub k squared over delta x plus 1 delta x here. Okay, so there we go. Now we've built an overall estimate for the length of the curve. Now, normally, our next step is to sort of take the limit of this as that delta x gets really small, as those sort of partitions get infinitesimally small, making it go from an approximation to an exact equality. The sort of hassle thing, though, is that we've got this delta x that's actually trapped inside this expression. Normally, we just have a delta x here, and then we can say, okay, this becomes the function we need to integrate, and then this is dx. But we've got this delta x that's also inside here. And hopefully we can see I should have extended these parentheses here and here to include that delta x down there as well. It's the entire expression squared there. So we need to examine this a bit more. So let's take a look at this term right here. So if we take a look at this thing real quick, this is f of x sub k plus 1 minus f of x sub k over delta x. So what is this actually calculating here? Well, what it's doing is it's calculating the change in f, or the change in y, if you want, divided by the change in x. So this is something you guys know. This is what we call the average rate of change. It's how much did we change in y over how much we changed in x. And we have a really nice theorem that tells us something about the average rate of change. It tells us that there must be some point where the derivative is equal to that average rate of change. And this is what we call the mean value theorem. This is the mean value theorem back from Calc 1. It says that there has to be some point, x sub k, we're calling it x sub k star, where the derivative equals the average rate of change. And this x sub k star with x sub k star, an element of that x sub k to x sub k plus 1 interval. So in other words, there's some value in our interval where if you take the derivative of the function, it exactly matches the average rate of change. That's the mean value theorem. Okay, so now, instead of having this whole mess, we can replace it with the derivative. So let's give ourselves another page here and realize that now we can say that that length is approximately the sum over all these x sub k, the square root, f prime of these xk star squared plus 1 delta x. Now we have a much nicer expression. Now we can use our standard trick to get rid of this as an approximation. We can say that L is equal to the limit as delta x goes to 0 over all these x sub k square root f prime x sub k star squared plus 1 delta x. Now normally these x sub k's are the same as these x sub k stars. This time they're a little bit different. These x sub k's technically reference the endpoints of each partition. These x sub k stars are some value guaranteed to exist by the mean value theorem. But it turns out not to matter because delta x is going to 0, meaning that the partitions, their width, is becoming infinitesimally small. So while these are slightly different than this, they're all getting squished together, and we know we're going to be evaluating over every value, so we can still change this into our definite integral. We can say that the length here is going to be the integral from a to b, because that's the bounds of our interval here, of the square root of f prime of x squared plus 1 dx. So in other words, to determine the length of a curve, you integrate from a to b the square root of the derivative of the curve squared plus 1 dx. Now, oftentimes, we derive this result, and this is absolutely correct. Oftentimes, people like to rewrite this as the integral a to b square root 1 plus f prime x squared dx. They like the 1 first and then the f prime second. And then sometimes you will also see this rewritten, and this last form is how we're going to actually write out in our summary, where they replace the function notation for the derivative instead with the dy dx squared dx. And again, all of these three forms here are all the same, so it doesn't matter which one you decide to remember. Just be aware that this is the one that your textbook uses, and it's also going to be the one that we use in summary. This is just sort of the more common notation, though these are, of course, exactly similar. Okay, so to quickly summarize our derivation here, our main idea was to take a look at sort of trying to determine the length along a curve. To do that, we took one piece, and we examined the straight line distance. So we first examined the straight line distance between 2 points on our curve. We found that using the distance formula, we could express that straight line distance like this. Then we did this somewhat weird manipulation where we factored out delta x squared out of the square root. That put a delta x here, and then built this sort of bizarre fraction here. Then we said, okay, we can go ahead and get an estimate for the overall length by just taking the sum of all these straight line pieces. But then we said we needed to deal with that sort of weird looking fraction because we had never had a delta x show up inside what we eventually thought would be the function we're going to be integrating. So we analyzed this. We used a very clever application of the mean value theorem, which told us that that fraction was actually equivalent to the derivative at some value. We don't know what that value is, but we know it's in that interval. So we were then able to replace it as the sum of the square root of the derivative squared plus 1. We did our standard trick of letting the limit as delta x goes to 0 so that it was no longer an approximation, became an equality. And then we just rewrote it as a definite integral here. Okay, so let's go ahead and quickly summarize these results then. So for the summary here, suppose we have a continuous function f of x on the interval a to b. Then the distance from the point a f of a, b f of b, along the curve f of x, which is called the arc length of that curve from x equals a to x equals b, is given by the expression we just determined, the integral from a to b, square root 1 plus dy dx squared dx. Again, the visualization of what you're measuring here is if we have our curve, there's a, there's b, we are measuring the distance from this point along this path. So we are measuring a longer distance than just the straight line. We're measuring if you were following this path there. Okay, we're not going to reprove, but you could do all this from the y perspective. So if you had a function of y, you could redo all of this in terms of y. So this is just an alternate statement with respect to y. So if you have a continuous function g of y, I guess back up here I should label this. We're going to call this f of x here. So if you have a continuous function g of y on the vertical interval c to d, so the y interval c to d, then the distance from the point g of cc, g of dd along the curve g of y, which is again called the arc length of g of y, is given by the exact same integral, except that you do the derivative of x with respect to y squared dy. So it's the same formula, just done with respect to y. The visualization here would be that you'd have some curve. Maybe we have something that looks like that, and you're going from C to D here, and you're thinking about this curve not as a function of x, but as a function of y. So that's g of y. And again, you're measuring the distance as you go from that point to this point here along that curve. Okay, so now we have a new geometric sort of idea, the length of a curve, that we can determine using a definite integral. So if you put this together back with what we were doing in chapter 6, we now know how to use definite integrals to handle areas, volumes of solids of revolutions, and distances along curves, which in some way tells you that we now understand how to use integrals to help us with two-dimensional things, area between curves, three-dimensional things, volumes of solids of revolution, and one-dimensional things, lengths of curves. So integration can help us with a ton of different geometric ideas. All right, let's get into taking a look at a couple examples then. So the first thing we'd like to do is we'd like to determine the length of the curve y equals x squared from x equals 0 to x equals 1. Now, in terms of a formula, the arc length formula is pretty straightforward. So we could just jump right in and plug into our formula and just work through the definite integral. I am going to just hold off for 1 second because I would like to go ahead and at least do a little bit of a visualization just to really make sure we're clear on sort of the geometric idea that's behind this. So let's take a quick look at sort of a diagram here. So if we go ahead and we sort of diagram out what we're looking at, should be very simple here. There's x equals 1, say there's y equals 1. We're going from x equals 0 to x equals 1, and we know that when x is 1, y equals x squared is also going to be 1. So we're just following the parabola that goes like that, going from 0, 0 to 1, 1. So this point down here, that's 0, 0. This point right here, that's 1, 1. Okay. Now, before we calculate the length of this curve, so this right here, what I'd like to do is a couple little estimates. Let's first do the straight line distance. So the straight line distance like that. So that length would be very clearly the square root 1 minus 0 squared plus 1 minus 0 squared. Just taking the difference in the x-coordinates squared, difference in the y-coordinates squared, adding them together. You should be able to easily see that the straight line distance is root 2. Why am I bothering to do this? Well, because I know whatever the answer is that we get for the length of our curve has to be bigger than root 2. Because one geometric fact is straight line distance is always the shortest. So if we're going along some non-straight path, it has to be greater than root 2. Now, let's see if I can come up with a upper bound. So you can sort of think of L equals root 2 as a lower bound. So let's think of sort of the dumbest path we could take from here to here. Well, instead of going in the straight line, which would be the most efficient, we're going a little less efficient. What if we went like this? We went this way, and then we just went up there. Now, it should be very clear that that is 1 unit this way, and then 1 unit that way. So that length would be 2. You can sort of think about that as the worst case, right? You just walk all the way to here, and then you walk all the way there. It would be identical if I went this way and then this way. Why am I bothering to mention these? Well, it should be clear that our length is going to be trapped between these. We should see that our length, the arc length, is going to be somewhere in between root 2 and 2. It's going to be not as efficient as that, but it's not going to be as long as that either, right? It's slightly bowed out, so it'll be a slightly larger than root 2, but it won't be as large as 2. So I'm just trying to get you guys to understand some geometric bounds to understanding what the possible arc length could be. So at the end here, we'll actually check that the value we got is somewhere between root 2 and 2. All right, so how are we going to actually calculate the arc length here? Well, we're going to use our arc length formula. It's going to be the integral from 0 to 1, because those are our x bounds, square root 1 plus. Then we need to take the derivative of this. It's already in terms of x, so we might as well work in terms of x. So we take the derivative, that's 2x, and then squared dx. So there we go. That's the definite integral. If we were only interested in setting this up, we would be done right here. But we do want to try to evaluate this. So if we are trying to evaluate this, we'd have the integral from 0 to 1, 1 plus 4x squared dx. How are we going to integrate this? Well, it's been a while since we did techniques of integration, but this is a number plus a square in there, inside of a square root, so we're probably thinking trig sub here. So we might try a trig sub. Since it's 1 plus something, we want to use tangent, but we do need to get rid of that 4 there. So we might have to do something like 1/2 tangent theta. The reason I'm choosing 1/2 tangent theta is so that when I square it, this will become a 1/4 and it'll cancel out there. I'll also have to get my dx, which will be 1/2 secant squared theta d theta. I should also change my bounds. I had 1 and 0 for x. Now I need to think of theta. A little bit harder to change bounds here because I'm going to have to do 1 equals 1/2 tan theta, which I guess tells me that my new bound here is going to be arctan of 2 And here, 0 equals 1/2 tangent. Solving that, theta equals arctangent of 0, which is 0. So my new bounds are going to be from 0 to arctan of 2. All right, let's go ahead and plug this stuff in there. Integral 0 arctan of 2, square root 1 plus 4. Plug in your 1/2 tangent theta, so 1/2 tangent theta squared. And then for this dx here, we'll have 1/2 secant squared. So 1/2 secant squared theta d theta. All right, now we can go ahead and simplify. 0 arctan 2. Looks like in here we will get 1 plus tangent squared theta. And out here we have 1/2 secant squared theta d theta. Again, that's just because 1/2 squared is going to be 1/4. That'll cancel out, and we have our tangent squared. Now, this is why we chose tangent. 1 plus tangent squared is secant squared. So we get L is the integral from 0 to arctan of 2, secant squared theta. Of course, we still have our square root, and we have a 1/2 secant squared theta d theta. And, of course, this is going to become a secant theta. That'll mix with this secant squared, and it looks like we now have the integral from 0 to arctangent of 2, 1/2 secant cubed theta d theta. All right, let's grab this and move on to another page to actually finish up evaluating here. Okay. So, if we go on to our next page here, all right. We might want to try to remember how we sort of deal with different powers of trigonometric functions. Unfortunately, secant cubed is one of those special ones where we actually just derived a result for secant cubed. Secant cubed actually required an integration by parts and then a manipulation, but it is one that we just wrote down a expression for. So if we remember what that expression was, we can get that this is going to be 1/2 times 1/2, and the actual integral of secant cubed is 1/2 secant theta tan theta plus 1/2 ln secant theta plus tan theta, evaluated from 0 to arctan of 2. So this right here, 1/2 secant theta tan theta plus 1/2 ln secant theta plus tan theta, that was our derived result for the integral of secant cubed. We still have that extra factor of 1/2 there, and we still need to evaluate this from 0 to arctan of 2. So plugging that in and distributing a little bit, it looks like we have 1/4 secant of arctan of 2 tangent of arctan of 2 plus 1/4 ln secant of arctan 2 plus tangent arctan of 2 minus, and now we'll put some parentheses, 1/4 secant 0 tan 0 plus 1/4 ln secant 0 plus tan 0. Now, of course, right here, this would be good enough, right? I mean, this is our value. There are some simplifications here. Tangent 0, of course, all that is 0. Here, secant 0 is 1. Tangent 0 is 0. Ln of 1 plus 0, also going to be 0. So all this stuff is 0. So we can simplify this to 1/4 secant arctan 2 tangent arctan 2 plus 1/4 ln secant arctan 2 plus tangent arctan 2. Okay. Now we should be able to also recognize that tangent of arctangent is just going to cancel out, so these should be 2's. So we can get this to 1/2 secant arctan 2 plus, looks like 1/4 ln secant arctan 2 plus 2. Now, at this point, we could just leave it alone or just type it into a calculator. You can actually determine secant of arctan of 2. You can say, okay, this is an angle theta, such that when you draw your diagram, theta, it has a tangent that is 2, so 2 and 1. That means that this side over here, the hypotenuse here would be square root of 5, and you can use that to actually fill in secant here. But instead, what I will do is I'll just go ahead and type this into a calculator real quick, and we can go ahead and see what we get here. So we get 1/2 times the secant of tan inverse of 2, and then plus 1/4 times natural log of secant made a mistake there, I'm sorry, 1/2 times 1 cosine tangent 2, okay, and then plus 1 divided by 4 times ln okay. And if you do this, what you should get if you try it on your own is that this comes out as L being approximately 1.4789. If you compare that, right, root 2 is about 1.41, so you'll notice that RL is greater than root 2, check, and you'll notice that RL is less than 2, also check. So no need to really go all this way, but I just wanted to demonstrate that our bounds that we got here were actually accurate. Our length ended up being between root 2 and 2. Interestingly enough, though we won't do it because they get very messy, this guy was already pretty messy and it was only x squared. You guys should, or it shouldn't be hard to believe, that as you let this power get larger and larger, if you did this for x cubed or x to the 4th, then what happens is these curves get more and more similar to the actual length of 2. And actually, it's a very interesting result, and you can think about why it would be true, or you can draw some graphs on your own, that if you examine these arc lengths of x to the n, and you look at the limit as n goes to infinity, the lengths actually do approach 2. We saw that for this case is actually quite similar to the straight line distance because x squared isn't that curved. But if you do x cubed, or then x to the 4th, or x to the 5th, or x to the 6th, they get steeper and steeper, and they get more and more similar to that green distance of 2. So there's some very interesting things going on with these geometric ideas here. All right, for now, though, let's try a couple more examples of computing these arc lengths. All right, let's see if we can determine the length of the curve y equals 2x minus 3 to the 3/2 from x equals 2 to x equals 6. Since I think we've discussed enough about this sort of geometry, we can just jump straight to sort of applying our formula and looking at how the integration should run. Everything is in terms of x, so we will do this in terms of x. We'll have the integral from 2 to 6, square root, 1 plus. We need to take the derivative here. We can do that off to the side if we want. If we have this here, we can easily see that dy dx. We drop that 3/2, 2x minus 3 to the 1/2, chain rule times the derivative in the inside, 2. So that means it looks like we'd get 3 times 2x minus 3 to the 1/2. So let's go ahead and pop that in. So 3 2x minus 3 to the 1/2, all squared, dx. So that is the setup for the arc length there, 1 plus the derivative squared with respect to the variable we chose. We can simplify. That's the integral from 2 to 6, square root, 1 plus. If we distribute this square, we should get a 9, and then 2x minus 3. Because this square will hit the 3 and become a 9, this square will hit the square root, cancel out. Okay. Then we can simplify. Looks like we should have the integral from 2 to 6, square root, looks like 18x from our 9 times 2x, and then minus 27 plus 1 sounds like minus 26 dx. How are we going to integrate this? Well, now we've got this square root here, but we don't need to use trig sub because this is just linear. So we can get away with just a normal u sub, 18x minus 26. du will be 18 dx. So we'll get a 1 over 18 du is dx. If we change our bounds, 6 and 2, plugging in 6 there, 18 times 6 minus 26. Looks like our new upper bound is 82, and then 18 times 2 minus 26, new lower bound is 10. So we now have the integral from 10 to 82. We have a 1 out of 18 in front, and we have a u to the 1/2 du. We integrate that. This is going to become, if we add 1, a 3/2. So we need to multiply this by 2/3. That sounds like that's going to be 1 out of 27, u to the 3/2, evaluated from 10 to 82. And if we plug that stuff in, looks like we get 1 over 27, 82 to the 3/2, minus 1 over 27, 10 to the 3/2. So that's the length of this curve from x equals 2 to x equals 6. If you want, on your own, plug in x equals 2 and x equals 6 into this, get the 2 points, measure the straight line distance using the Pythagorean theorem or the distance formula, and you will see that the result that you get there is smaller than this, because the straight line distance is always the shortest distance. For now, though, let's take a look at another example here. We'll do one from the y perspective. We'll determine the length of the curve x equals ln secant y, from y equals 0 to y equals pi over 4. So the only difference here is everything's in terms of y, but we can still go ahead and do this. So we can say that the length here is going to be the integral from 0 to pi over 4, since we're going to be working with respect to y. Then square root 1 plus. We'll need to get the derivative here, so once again we can sort of do that off to the side here. If we go ahead and do this, dx dy, so differentiating with respect to y this time, is going to give us 1 over secant y, that's the derivative of the ln, and then chain rule, secant y tangent y. Canceling that down, it looks like our derivative, dx dy, is going to be tangent y. So we can pop that in, tangent of y squared, and then we're integrating here with respect to y. So this is the arc length formula with respect to y. We did the derivative with respect to y. We have y bounds, and we have a function of y. So it works the same way. For now, though, we can go ahead and simplify. We have the integral from 0 to pi over 4, square root 1 plus tangent squared y dy. This square root often proves to be a problem. We've had to use u sub, we've had to use we've had to use trig sub, u sub. This time, though, we get away with dealing with the square root even easier. 1 plus tangent squared can just simply be reduced as 0 pi over 4 square root secant squared y dy. And then if we go ahead and apply that, we get the integral from 0 to pi over 4 secant y dy. Now that's nice because that got rid of the square root. The square root is often the thing that poses the problem computationally when dealing with arc length. But now we just have integral of secant, which we do know how to do. That's just going to be ln absolute value secant y plus tangent y, evaluated from 0 to pi over 4. If we plug those in, we get ln secant of pi over 4. Well, cosine of pi over 4 is root 2 over 2. So secant is going to be 2 over root 2, which is just root 2. So root 2, and tangent of pi over 4 is 1. So ln root 2 plus 1 minus ln 1 plus 0, because secant 0 is 1, tangent 0 is 0. This, of course, is 0. So we get ln root 2 plus 1. So the length of this curve from here to here is natural log root 2 plus 1. All right, we've got one final example just to see one other sort of computational trick that can sort of turn up when dealing with arc lengths. If you guys have noticed so far, in all these examples, actually setting up the integral is very easy. A lot of times when we were dealing with definite integrals for areas or volumes, the work was actually in just trying to figure out what the integral should be. For arc length, that's not the case. You have a very simple formula, you just plug in. More the difficulty is often in actually performing the integral because of that square root. And as we've seen here, the first 2 times we actually had to come up with some sort of substitution here, or in this one here, to deal with that square root. On this one, we got a bit lucky because we had a trig ID. I'd like to show you guys one other sort of instance that often arises with arc length. So for our last example, we're going to determine the length of the curve y equals 1 over 8x to the 4th plus 1/4 x to the minus 2 from x equals 1 to x equals 2. Again, setup should be very easy. We're going to have the integral from 1 to 2, square root, 1 plus. Need to go find the derivative of this, so let's go ahead and just do that over here. dy dx, derivative with respect to x this time, because it looks like everything's in terms of x. Drop the 4 down, looks like we should have 1/2 x cubed. Drop the negative 2 down, looks like we should have minus 1/2 x to the minus 3. All right, we'll throw that stuff in. So we have 1/2 x cubed minus 1/2 x to the minus 3. All of that squared. Got to remember you need to square the derivative and then dx out here. Now this is a mess in here, so probably at this point we look sort of stuck. So the best thing we can try to do is try to just multiply this out. So let's take a moment to multiply that out. 1/2 x cubed minus 1/2 x to the minus 3 times 1/2 x cubed minus 1/2 x to the minus 3. Well, this is FOIL. First 2 terms are going to make 1/4 x to the 6th. Then it looks like this, if we do this guy and this guy and this guy, the x cubed and the x to the minus 3 are going to cancel. So 1/2 and minus 1/2 is going to be minus 1/4. Then this guy and this guy, x minus 3 and x cubed are going to cancel. Minus 1/2 and 1/2 are going to be minus 1/4. And then the last, this and this, looks like we should get plus 1/4 x to the minus 6. If we simplify that, that looks like we get 1/4 x to the 6 minus 1/2 plus 1/4 x to the minus 6. So we can replace this with this. Doesn't look a lot better, but let's see what happens. So we now have the length is integral 1 to 2, square root. We still have this 1 here, and now we have 1/4 x to the 6 minus 1/2 plus 1/4 x to the minus 6 dx. Notice we get a small simplification. We can make that a positive 1/2 now. So now we have the integral square root 1/4 x to the 6 plus 1/2 plus 1/4 x to the minus 6 dx. Okay, at this point, it doesn't look so hopeful because inside the square root, it's definitely not linear, so we can't just do u equals this stuff because the du is going to be a horrendous mess. And it's not like an x squared where we can do a standard trig sub. So the only thing we can sort of hope for is that maybe this is secretly sort of similar to this. In other words, it already is a perfect square. 1 plus tangent squared didn't look like it, but it was actually just secant squared, and we could just directly apply the square root. It actually turns out that the same thing happens here. If you'll notice, this expression is identical to this, except that this one had a cross term of negative 1/2, and this had a cross term of positive 1/2. That means that this is actually the positive version of the square here. So we can actually rewrite this as the integral from 1 to 2, square root 1/2 x cubed plus 1/2 x to the minus 3, all squared. It actually is a perfect square. If you want, on your own, take this off to the side and FOIL it out, and you will see that it gets right back to here. The whole reason this worked is because initially we had that minus 1/2. We added 1, we got positive 1/2. That means we have the same terms, just with a positive in between instead of a negative. Now we have the square root of the square, so we can simplify. We get the integral 1 to 2, 1/2 x cubed plus 1/2 x to the minus 3 dx And now we're just in that nice straight up power rule. We can actually go ahead and apply the integral here. This is going to become an x to the fourth, so we get 1/8 x to the fourth. And then here, we're going to add 1, become -2. So minus 1 over 4, x to the -2, evaluated from 1 to 2. We can plug that stuff in. If we plug in 2, 16 over 8, that sounds like 2 minus 2 in here is going to be 1 over 16. And then minus, plug in the 1, 1/8 minus 1/4. And that would be the length of this curve from x equals 1 to x equals 2. So again, arc length, it's a similar geometric idea to how we used integrals for areas and volumes. The big difference though here is that unlike areas and volumes where a lot of the work was in just setting up the integral, here the work is often in actually trying to integrate it. Because again, integrating square roots is something that's sort of challenging. I tried to do this set of examples for you to see the standard techniques that are useful when dealing with arc length integrals. Sometimes you'll have to deal with what we dealt with in the first one, which was a trig sum. That'll happen if you end up with that 1 plus something squared, like that 4x squared there. Sometimes you'll get lucky and you can get away with just a u sub. If the thing inside the square root is still linear, then you can get away with a u substitution. And then the last two showed you ways of sort of getting a perfect square inside the square root so that you can actually remove the square root before integrating. So this actually wraps up everything we want to say about section 8.1, which is arc length. In our next video, we'll be moving into 8.2, where we will make use of arc length to go back to solids of revolution and study their surface areas.